In this video, we are going to discuss Euler tors. So let G be a graph. Throughout, we're going to assume actually that it's a connected graph. Then a sequence of vertices, V0 through Vk, is called an Euler tor if it satisfies the following properties. First, V0 is equal to Vk. Should note that these are vertices. Second, for every edge of the graph, there exists a unique index in the sequence such that the edge, uv, is actually, it has endpoints vi plus 1. In other words, every edge appears at a unique spot in the Euler tor. Finally, for every I, vi plus 1 is an edge. So the idea you're supposed to be thinking about is that this is a sequence of steps in a graph where you're traveling along edges. And it's okay to go back to places you've been before. The goal is to end up where you started and to cross every edge exactly once. Note that if you remove the second condition, you have what's just called a tor. So we say a graph is Eulerian if it has an Euler tor. So let's take a graph at random. If I were to give you this graph and ask, does it have an Euler tor? Well, it would be very hard. On the other hand, if I give you this graph, it wouldn't take very long to see that if I start at this vertex and just go down and around, and then go along the inside, I end up with an Euler tor. Note that I find it easier to label the edges in order and to label the starting vertex. And then that uniquely determines the Euler tor, because you already know the next vertex is to just go along the next edge. How about this one? Does it have an Euler tor? It's hard to tell. You can try tracing, and you will quickly get stuck without getting through all the possible edges. In this case, the theorem is that G, if you have a connected graph, then it is Eulerian if and only if the degree of every vertex is even. So I'm sure you've noticed by now there's an obsession with if and only if theorems in graph theory. The reason why is because you want criteria that are easy to check. So you want, if your statement is true, that it's easy to verify it, and you want that if it's false, that it's equivalent to something else that's easy to verify. So in this case, how can you verify it? Well, I could just give you an Euler tor. Now, how could I verify that it's false? Well, I can just point out that there's a vertex of odd degree. All right, so let's actually look at this theorem. Suppose I have a tor with the first and last vertex being the same. Note that that means that each consecutive pair forms an edge in the graph. For any vertex in my graph, consider the indices for which vi is equal to v. Then by definition, vi minus 1 and v have to be adjacent, and v and vi plus 1 have to be adjacent. So for every time I see v in my Euler tor, that corresponds to two edges in the graph. Now later, it could be a different pair of vertices, but I'm going to get a different pair of edges. But it's still the same one in the middle. And so the point is that if I look at the edges coming from this tor and call that T, I'm going to get a subgraph. So I'm going to call this subgraph VT, where T are the edges coming from the tor. Then the degree of V in this subgraph is even. It's actually twice the number of times V appears on the tour. So if there is a vertex in V of odd degree, then we see for any tour T, the degree in T is not equal to the degree in the original graph. In particular, G is not Eulerian, because the point there is if this vertex had odd degree, there would always be an edge left out of the tour. So that gives us one of the conditions. If you have an odd degree vertex, there are no Euler tours. Now we always get to the harder part to prove. Suppose the degrees are even for every vertex. How do you actually show there is an Euler tour? Well, we rely on the following lemma. If every vertex has degree at least 2, the smallest even number, then G has to contain a cycle. One way to prove that is to take the longest path possible in G. So if it's a connected graph, it has to have paths. One of them has to be the longest possible. That's not necessarily unique, just pick one of them. We'll take a vertex on the end. It has degree 2, so it has to have another edge coming out of it. That edge can't be to another vertex, because if that were true, then you'd have an even longer path, contradicting the fact that we picked the longest one. So any edge coming out of this vertex has to be going to another vertex already on the path. And so go along the path and connect those two endpoints, and you have a cycle. This works with the other endpoint as well. So actually you get at least 2 cycles, except in the possibly degenerate case where the 2 endpoints are adjacent to each other. But the point is we have at least 1 cycle. All right, so let's use this lemma. Let C be any cycle of the graph. Then if you delete the edges of the cycle from G, you're going to get a bunch of components. Since degree of each vertex on a cycle is exactly 2, then in this graph, you've either kept the degree of every vertex the same, or you've changed it by decreasing it by 2. So in this graph, every vertex is even degree. By induction, it is Eulerian. So it has an Euler tour. So the idea is that at each vertex, somehow you might have an Euler tour going on, or more accurately, in each connected component of this graph, you have an Euler tour. And so then the idea is that you just go along the cycle until you hit each component, then you do the Euler tour you already have for that component, and then you go along the cycle to the next component. And this is how you glue the Euler tours together. So let's look at that graph we had earlier. If you check the graph we had earlier, the vertices each have even degree. So according to the theorem, there must be an Euler tour. So our strategy is to take any cycle, delete it, and here are our components. Take another cycle, delete it. Here I'm ignoring the isolated vertices. Now I'm just down to a cycle, so I create an Euler tour. I should always label my starting point. Here I chose to start here, and I go 1, 2, 3. Now I go back up 1 level to this graph. So I'm over here, and the idea is I chose to start here and go this direction along my cycle. And so the first time I come into this component, I start by going along the Euler tour from this triangle. So you see I go 1, 2, and then now I use the Euler tour from this triangle. In reverse order, apparently, but that's likely just a typo. And then I complete the cycle from the red cycle. And so that's basically the idea, is that you're gluing the cycles together in a funny way to create a tour. Now let's add the blue cycle back in. Same idea. I've picked a starting point. I picked a starting point. I go along my cycle. The second I enter this component, I start copying this component down in order, which is exactly what I'm doing. And then keep in mind you can always change the order of an Euler tour. It's all based on where your starting point is. So note here, because I started here, the starting point became this vertex instead, which had the impact that the 2 became the first edge and so on and so forth, and this became the last edge. That explains that change. Now I just complete the cycle I had before. And so I end up with an Euler tour. To finish, I'll mention another concept in graph theory. It's called a Hamilton cycle. It's basically a spanning subgraph that is a cycle. So it's similar to an Euler tour. Instead of visiting every edge exactly once, you visit every vertex exactly once. Unfortunately, that's about where the similarities end. We don't have an if and only if result for Hamilton cycles. And so it's actually a $1 million question. Determine if a graph G has a Hamilton cycle. And as in, if you find an algorithm that can tell whether a graph G has a Hamilton cycle that runs quickly, you'll be a millionaire.